Hello, everyone. This is our first lesson covering a new overall topic called parametric equations. And specifically, we're going to talk about the basics and how to graph parametric equations. Now, in talking about this new topic, parametric equations, let's compare that with the equations that you've probably dealt with in your previous work. So equations so far, as in non-parametric equations, right? And if you think about it, the equations that you have worked with so far usually involve two variables, right? So one variable, usually we call x, and then another one, usually called y. And then, for example, you might see an equation like this, y equals 5x squared plus 1. And as you can see, both variables are involved in the equation, like x here, y there. And in the past, you've probably worked with many different equations of this kind. You've probably done things like graph equations like this, solved for something in the equation, rewritten the equation, etc. But now compare that with parametric equations. And the parametric equations that we'll be working with in this lesson will, in fact, involve two variables, x and y. But we're also going to introduce another variable, a third variable, and usually it'll be called t. And then what do the equations actually look like? So usually you'll be working with more than one equation at once. So here's an example. It's a set of two equations, right? And what's going on here is the first equation involves the variables t and x. And then the second equation on the bottom involves the variables t and y. And these parametric equations are actually super useful and super powerful. For example, they're useful in modeling motion. So like modeling or calculating how things move in 2D or even 3D space. Now, just to illustrate the power of parametric equations, let's compare graphs between non-parametric equations and parametric equations. So probably in your previous work, you've spent a lot of time graphing different types of equations, right? All kinds. So here's just a couple of examples. We've got a parabola, a rational function, a sine function. And if you think about it, these graphs are limited a certain way. And it's because for each x value, there can only be one y value. And if you remember from your previous work, that is a feature of functions, right? Y being given as a function of x. And you might remember something called the vertical line test. So non-parametric equations, many of the ones that you've worked with only give graphs that have to pass the vertical line test. So like if we do the vertical line test in certain locations real quick, right, each graph only crosses the vertical line in one place. And in many cases, these non-parametric equations are limited to this kind of graph. A lot of the time, they can only produce this type of graph. So now compare that with parametric equations. And actually, the graphs that we were just talking about, parametric equations can do all of those. And parametric equations can do so much more. So as an example, with parametric equations, it's easy to graph a full circle. And right off the bat, this is an example of a graph that fails the vertical line test, right? Like if I draw a vertical line, then the vertical line crosses the graph at two locations. So that is a graph that in some sense is more difficult to generate with a non-parametric equation. And then there's many other crazier examples. Like look at these. All kinds of stuff going on there. So again, parametric equations, they open up more possibilities. They expand our ability to graph different kinds of shapes. Now, just a little bit more comparing, let's think about how you've worked with equations in the past. So typically with the equations you've worked with in the past, there were two variables. As usual, we'll call them x and y. And then as an example, let's consider the equation y equals x squared. And so this equation relates the two variables, x here, y here. And you can think of this equation as a function. So this gives y as a function of x. And so in the past, you might have been taught to think of y as depending on x. So we call y the dependent variable and x the independent variable. Y is dependent. It's dependent on x, so x is independent. And then we can also think of x being the input. And then, for example, we could pick a bunch of x values to plug in as inputs here. And then our equation or function outputs that as values over here as y values, right? So we can think of y as the output. And then to graph this equation, you might make a table of points using those input and output values. And so remember how we do that. So let's say we're looking at the input values, the x values from -3 to +3. So -3, -2, -1, all the way to +3. And then how do we use these x values to find the corresponding y values? Well, so with like -3, for example, you plug it in for x, so you get y equals -3 squared, which is just +9, right? So 9 here. And then what about the x value -2? Plug it in for x, y equals -2 squared, which is just +4. And of course, you could go on and do that for all the x values, and you would get the following. So these are the values. And remember, each xy pair represents a point on the graph. So -3, 9, for example. That's a point on the graph, and we can just graph it, -3, 9. And then you would do that with all of these points, right? -2, 4, -1, 1, 0, 0, etc. So here they all are on the graph. Also, don't forget, we could find x and y values between the ones we have here, right? We could graph more points in between. So basically, this graph is a continuous curve of points like this. And if you remember from your previous work, this equation, the graph is a parabola. So now the new stuff, parametric equations. And we saw before that we're going to have 3 variables now. Just know that you can have even more, but we will stick to just 3. And we're going to be graphing this set of equations on this coordinate grid here. But notice that the axes are the same. So we've got x on the horizontal axis and y on the vertical axis. And there is no t-axis. So how does t work? So know that in this situation, both x and y are dependent variables. So these are both dependent. And so what are they dependent on? Well, if you look at our 2 equations here, you can see, okay, x is given by a formula involving t, right? And y is given by a different formula involving t. And so x and y both depend on this other variable t. They're given in terms of this other variable t. And t is our one independent variable. And we call this variable t a parameter, or the parameter in this case because there's only one. In general, you can have more. And so now let's go ahead and graph this. So what you do is, again, you make a table. And in this example, we're going to do -3 to +3 for the independent variable again. -3, -2, all the way to +3. And by the way, this t is our input now in this situation. So these t values are our input values. And we've got 2 equations. So these 2 equations are going to give us 2 outputs per t value. And how you calculate this, So for example, this first t value, -3, we're going to plug that in to get an x value for that t value and a y value for that t value. So the x value, it says x equals t squared minus 4. So plug in -3 for t here, and then the right side, evaluate that, and that'll be our x value in this case. So for example, x equals -3 squared minus 4. -3 squared is 9 minus 4 is 5. So we've just found that for this input value, the output value for x is 5. What about y? So plug in t here, that gives us y. Y equals 3 times -3, that's -9. Be careful with positives and negatives. So the output value for y, the y value is -9. And of course, you would do this for all the t values you're looking at. And you should get a table like this. But how do we graph this? So know that each xy pair actually gives us a point like before. So this first row, t is -3, x is 5, y is -9. Well, the x and y part gives us a point. So x is 5, y is -9. Where is that? +5, -9. That's this point right here. And like I said before, there is no t-axis, so t doesn't really show up on the graph. So let's label each point that we get with the t value that we use to get that point. So this point 5, -9, we plugged in -3 for t to get that point, right? So this is the point on the graph when t equals -3. What about t equals -2? So we got the point 0, -6. Where is that? X is 0, y is -6. So here. And what was the t value there? T was -2. What about when t is -1? So the point is -3, -3. So the point is here. Again, t is -1 there. And so we use this process to graph all the points, like so. So we had 7 t values, we graphed 7 points. And like before, don't forget that we could find in-between points, like t equals 1.5, for example, and we'd find that this is a smooth curve, right? We can connect the dots with all the little points in between the ones we graphed. And you can kind of see this is a sideways parabola. Now, that's how you graph these parametric equations, but think about this. So x and y, those are our outputs, right? And you can think of them as variables in space, spatial variables. So x and y values give us points in this 2D space, right? But then there's no axis for t, there's no t-axis. So you can think of t as actually being a time variable, and you can think of this curve as being the path of an object as time goes by. So for example, let's say there's this object moving around, and at t, time equals -3 seconds, the object's position is here. And then 1 second later, at t equals -2 seconds, its position is here. Then 1 second later, here, and so on. So we can think of this object moving over time along this parabolic path, this parabolic trajectory. Like this. So here's that same graph animated in Desmos. And if you've ever seen how things are animated, right, animations, you can kind of think of this graph as our taking this object and animating it, right? And so each point on this graph is like a frame in the animation. Now, a quick word. Here's an example. It says, fill out a table and construct a graph for the parametric equations shown. Work in radians. So this problem is just like the one we just did, although it uses function notation. So x of t is given by that, y of t is given by that. But this is no different from the previous example. It's just saying x is given as a function of t, y is given as a function of t. And another thing is, as always when graphing, don't be afraid of weird numbers. So this set of equations has cosine and sine. So it's very likely that you're going to get a bunch of messy numbers. And don't let that stop you from graphing. Just estimate where that point goes. So our first t value is 0. If you plug in 0 for t here, plug in 0 for t there. Actually, this first row you'll get clean numbers. So x will be 6, y will be 0. But then a lot of the other numbers, they won't be so clean. So for example, t equals 0.5, you get around 5.265. Don't forget to have your calculator in radian mode. And then for y, you'll get around 3.366. Next row, around 3.242 for x, around 3.637 for y. So again, very messy numbers, and you're just going to have to estimate them on the graph. Well, 6, 0 is easy for t equals 0. But then for t equals 0.5, that would be around maybe like here. So that's when t is 0.5, and so on. So if you do the whole table and the whole graph, so you should have got something like this. And you know, you don't always have to label the t values for each point, but think about this. These are only part of the points, and this should be a smooth curve that we're going to connect here, right? And we said this is like animating an object that's moving around. So you have to keep in mind the t values and figure out what order to go through the points. There's a direction, a set path as to how we connect the points. Because this object that's moving around starts at t equals 0, and then we need to go through an order next to t equals 0.5, then to 1.0, then to t equals 1.5, then to 2.0, and so on. These t values, it's like the passage of time, right? We start at t equals 0 seconds, and then time moves forward in order. And we increase in the number of seconds the amount of time that has passed. So there's the set path or order of movement that we have to follow. And if we do, then the curve looks like this. Starting at t equals 0, if we graphed all the points in between, then the curve looks like this bow tie thing. Like so. And you know, because we're only graphing so many points and we're graphing by hand, the curve looks, wobbly and crooked. But if we were to graph more points and we graphed it more and more precisely, then you would see that this should be a smooth curve that is also symmetrical. So here's the graph animated in Desmos. Goes like this, then like that. And as I said, the graph is smooth and is symmetrical. And you know, Desmos probably graphs a lot more points than we did by hand just now. So that is it for this lesson. As always, if you have any questions or feedback, feel free to contact me.